Okay, here's what we're going to be going over today. Section 1.9 is all about inverse functions. So we will learn how to use graphs to verify that two functions are inverse functions of each other. I'm going to show you how to verify that two functions are inverse functions of each other. It says analytically, probably a better word is algebraically. Okay, algebraically. And we'll also get to the horizontal line test. I can use the horizontal line test to determine whether functions are indeed one-to-one functions. Okay. So the main concept of inverse functions is really kind of undoing the operation. Okay. There's this little example. It's kind of hard to see with this font, but it says, you add 4. Well, how do you undo that? You subtract 4. Okay. Here's one's a little bit easier to read. Let's take a look at the second example. Let's just say your function that we begin with is 3 times x. Well, it's inverse notation or opposite operation is to divide. And here's the notation of it. This is how you show that something's an inverse. You do f and you put this little -1 up in the exponent area. So this means the inverse of f is equal to x divided by 3. There's a pair of inverse functions. Okay? And this can get a little confusing. What they're trying to show you here is whatever the domain of function f is, happens to be the same set of values of the range of the inverse. You kind of interchange them. You interchange the domain and range. Probably a good thing just to write in right here. So we want to interchange the domain and range. Look at that, even rhymes. Which also means the x and y values. So we're also going to interchange the x and y values. By interchange, I mean when we go from original function f to its inverse, we just switch them around, interchange them, okay? Okay, here's a graphical representation of function f and the inverse of function f, okay? Notice that they are symmetric to this line y equals x. That's always going to be the case. Write this down. Always symmetric to y equals x if they are inverses. Okay, so the line y equals x, just remember, that's just 1x plus 0 if we throw in the mx plus b style of that. So it's easy to graph. You just go to your y-intercept of 0 and you go up 1 over 1, and you could quickly get this line to check to make sure they look like they're symmetric. Okay, so that's how we'll use that property. Okay, so here we go. Let's start with number 1. Use the graph of function f, which is given right here. So let's label this right now. It does continue, by the way, this way. This is function f. To sketch the graph of its inverse function, then once we have that done, we'll state the domain and range of f and its inverse. Okay? All right, so here's how we'll use the graph of f to get its inverse. Quite simply put, if we just remember that the domain and range interchange and the x and y interchange, that's usually enough to figure this out. So let's be real specific on this first one. Function f contains, there you go, you can see now. F contains what? Well, we can just pick these off from the graph. It contains the point 0, 2. It contains the point 1, 3, 4, 4, and 9, 5. Okay. So if that's the case, we know, or therefore, the inverse contains, all I'm going to do is take these ordered pairs now and interchange the domain and range. So if f contains 0, 2, its inverse must contain 2, 0. If 1, 3 is on f, then 3, 1 must be on the inverse. Okay, everybody got that? And sometimes they don't like make them stand out. You might just have to kind of pick those points on your own. It might just be a smooth curve. But just grab some points, interchange them, and then start plotting them. So 2, 0. Let's plot these 4 points now. Okay, 3, 1. 4, 4, they share, and then 5, 9. Okay, so here's the inverse graph now. Okay, this is drawing the line y equals x too, just to make sure that it looks symmetric. So I start at the origin, I go up 1 over 1, up 1 over 1. And that should be enough to kind of get this diagonal line that splits the first quadrant. So then if you turn it sideways and check, do these look symmetric over that line y equals x? Yep, they do. So it verifies that you did it right, okay? All right, then the second part says state the domain and range of f and the inverse. So let's just squeeze this in right here and let's start function f. Domain and range. All right, so remember for domain, we're looking at the possible x values. For what values of x does the graph exist? So I'm just looking at this original black graph right now. Okay, ignore the blue line. We're just looking here. Where does this graph start for x values? It starts at 0. Okay, so 0 on to infinity. Looks like we should include that point. It clearly starts there. So we say bracket 0 to infinity. For range, remember a good idea sometimes to turn it if it helps. Okay, so it starts at a y value of 2 and continues this way for y because it's going to continue to extend this way. So 2 to infinity, including 2. Okay. The inverse, domain and range. Okay, now if you're doing this right and you're confident you have the graph correct and you did this part right, you could just interchange them. But let's look at the graph to make sure. Here's the inverse graph. The x value of 2 is its beginning point, and then it continues this way. So it is 2 to infinity, which matches up with the range of the original function. And then the range, the y value starts at 0 and goes up. Remember, you can use the turn sideways approach if you need to. This is 0 to infinity. Okay. All right, I'll pause right now and let you try number 2. Go ahead. All right, here's your feedback. Since we know f contains these points, we know the inverse must contain these. Okay. So plot those points and you get this. Does it appear symmetric to the line y equals x? Sure does. Okay, so domain and range. Here they are. Function f, 0 to infinity, and then the range up and down, -4 on up. Okay, make sure that matches up with your inverse, which it does. Okay, any questions on 2? Okay, here we go, on to the next learning target. This is a way to verify that functions are inverses of each other. And we're going to use composites. So from section 1.8, if I can take g of x, plug it into f, and it simplifies to x, and vice versa, f goes into g, simplifies to x, then they are going to be functions or inverse functions of each other. Okay, so if that happens under those conditions, they are going to be inverses. Okay, here they just kind of put the inverse notation spin on it, right? So f inverse into f and the original into the inverse. If you get x, they are inverses. Okay, so here we go. Let's take a look at example 3 and 4. It's actually a big part of your assignment today, are these two. 1 and 2 will be a little bit, but actually you'll see a little more of that tomorrow. All right, so algebraically, verify that f and g are inverse functions. Okay, now graphically, I'm going to demonstrate this to you, but it's not really a required step. I'm not going to make you write this down or put the graphs down on paper. The graphs that you'll do are more like examples 1 and 2. So when it says graphically, I recommend you just kind of use your graphing calculator, but you don't need to put this on paper in your assignments. Okay? Kind of an optional thing. If you don't have a graphing calculator, okay, it's an advantage if you do. Or you want to use metacalculator.com, throw it in there to verify you see the symmetry. Okay, so the algebraic part of this, here's what we're going to do. We're going to do just this. We're going to check that G can go into F and we can simplify to X. And then the other direction as well. Just start one at a time. Okay, so if G has to go into F, then I'm taking this function here and I'm going to throw it in right here. So that's going to look like this. 3 times X, but instead of X, I need to throw in all of G of X. Okay, so there's 3x minus 4, but instead of X, I threw in G of X there. Okay, and then just go through the steps that make sense algebraically. We can't subtract the 4 right now because it's being multiplied by 3. So a good thing to do right now, since I have a whole number times a fraction, is I put this over 1 to get things lined up. Sure, when you multiply fractions, we are supposed to multiply straight across, but if you see an opportunity to reduce it ahead of time, which is sometimes called cross-reducing, do that to make your job easier. These 3's will divide out. And we can replace those with 1. So since those cross-reduce, what am I really left with now? I've got 1 out front times just x plus 4. So that result is just x plus 4. Okay, so it's minus 4, but I'm talking about this first product. Okay, so rewrite it after the first step. Now I can move on to taking care of the minus 4. And when I combine these, of course, we just get 0. 0 plus x is x. So far, so good. You do have to do the other direction, though. If they ask you to verify, reverse the composite as well. So now we're going to do G composed with f of x. Okay, so now if f goes into G, this is going right here. Okay, so 3x minus 4 needs to go in that numerator. So I've got 3x minus 4 plus 4, all of it's divided by 3, like that. Okay, you could have options here. I could divide everything by 3, but that actually takes longer. When you have a messy numerator or denominator, it's always best just to clean up that numerator or denominator. Almost like you have an extra set of parentheses here. There's a way to kind of go through your order of operations. Okay, so let's go ahead and take care of this negative 4 and positive 4. Okay, that'll give us a 0 plus 3x. So now I just have 3x up top divided by 3. And now we can do 3 divided by 3, which is 1, and I get 1x. Okay, so we just verified graphically that these are inverses. Occasionally, they might give you some that you end up getting like x plus 10 or something, and then we'd say they're not inverses. But they both worked out to be x, so they are inverses of each other. Okay. Okay, 4 gets a little messier. Probably none of your problems will get much messier than 4. They all have a little different look to them in different order. So why don't you try to at least start the substitution, see if you can figure out the order of simplifying, and then I will intervene and help. Go ahead. All right, so here we go. G goes into F. So this entire cube root needs to go right there. So it's 2 quantity cubed plus 1. Okay, definitely can't add 1 or multiply when I've got an exponent here. We got to follow the order of operations. So don't let this inside bother you. Think about what happens if you cube something and then go back and, if you cube root something, then you cube it. They're going to cancel. Those are inverse operations. So that's gone on the first step. So then you rewrite it and you have x minus 1 over 2 left. Okay, now multiply. So put the 2 over 1, cross reduce that, and what are you left with? X minus 1 plus 1. Okay, and those cancel out to give you x.